In the last lecture, we have discussed about the sigma and pi bond formations in benzene. Now we will discuss about the detailed structure of benzene and we will study about its aromaticity. That these were the sigma bond formations and this was the pi bond formation. So, if we write benzene like this, the pi bonds are formed between these p orbitals. Each carbon has a p orbital which are parallel to each other. Okay. So, pi bonds are formed like this. Okay. So, here the pi bonds were formed between, if we do some numbering, 1, 2, 3, 4, 5, 6. So, it is between C1, C2, C3, C4, C5, C6. This was our structure 1. Now, if resonance happens, so if resonance happens, we can write the pi bonds like this. One, 2, 3, 4, 5, 6. Okay. Now, this bond shifts here. So, double bond is formed between C2 and C3. This bond will shift here. So, another is between C4 and C5 and this will shift here. So, another is between C6 and C1. So, this is the pi bond formation and resonance in benzene. Now, if you see that this is the benzene ring is planar, okay. Benzene ring is planar, that is it lies in the same plane. All the carbon bonds, all the carbon atoms and their bonds, they are in the same plane. So, benzene ring is planar and there is electron clouds on top and bottom of the benzene ring because of these p orbitals. So, p orbitals have two lobes, one is above the ring and one is below the ring. So, electron cloud is present on both sides of the ring. Okay. So, benzene ring is kind of like this. So, if this is the planar ring, there will be one electron cloud above and one electron cloud below. That is, for these rings there will be one electron cloud and for these lobes there will be another electron cloud. Okay. So, basically the benzene ring is present between two electron clouds. So, this was the structure of benzene. Now, we will discuss its aromaticity. Before that, so we have to discuss the bond lengths and bond strengths. So, bond lengths are revealed by XRD, that is X-ray diffraction analysis. So X-ray diffraction studies reveals that benzene is planar and the bond lengths. Now bond length of benzene reveals a very interesting character. We know that the bond length of single bond is 154 picometer and the bond length of double bond is 133 picometer. Okay, but bond length of benzene carbon carbon bonds is 139 picometer. That is, it is not similar to double bond or single bond. It lies in between. So, in between single and double bond. It is kind of described like this. It is called a partial double bond. This also proves that the double bond of benzene can interchange their positions. Since the double bond of benzene interchange their positions, so all the bonds contain a partial single and partial double bond character. So that is why the bond length of the carbon-carbon bonds of benzene are somewhere between the standard bond lengths of single bond and double bond. Okay. So this is the partial double bonded nature of benzene. So since there is an absence of pure double bond, benzene do not easily show addition reactions. We have seen that for alkenes and alkynes, addition reactions were a very crucial property, but for benzene it is not so. Because for alkene there were pure double bonds, but benzene double bonds are partial. That's why that they do not show addition reactions. Now we will discuss about the aromaticity of benzene. So the word aromaticity, as I had discussed when we had introduced aromatic hydrocarbons, that it derives from a word called aroma. We know that aroma means pleasant smell. So probably the first hydrocarbons of this nature that were discovered may contain some pleasant smell, for which these category was named as aromatic hydrocarbons. But to be honest, maximum compounds of this category do not contain any pleasant smell. Rather, aromaticity is a specific kind of characteristics of the molecules that makes a compound aromatic, non-aromatic or anti-aromatic. So, aromaticity is governed by a set of rules. So, the first rule is the compound aromaticity is applicable for ring structures. Okay. So, the molecule should be planar and cyclic. Okay. So, first of all, the rules of aromaticity are applicable only for cyclic and planar compounds. If a molecule is planar but not cyclic, then it is not applicable. If it is cyclic but not planar, then also it is not applicable. The rules will be applied. The first and foremost condition is the molecule should be both planar and cyclic. The second property is complete delocalization of pi electrons in the ring, or pi electrons should be or should show complete resonance. Okay. So, all the pi bonds that are present in the ring should be completely delocalized. What does it mean by delocalized? Let's say we have this cyclohexene. Here the pi bonds cannot show resonance. Okay. So, if we number the carbons like this double bond cannot interchange its position with any other double bond because there is no other double bond present, or even if it was present here, then also there is no mode of delocalization. So, these double bonds are called localized. These are localized double bonds or localized pi electrons. Okay. But let's say if we have this system, then it can be delocalized, right? It can be like this. So, this is called delocalized. Okay. The third point is if the ring contains 4n plus 2 pi electrons, then it is aromatic. Okay. 4n plus 2, where n is equal to 0, 1, 2, 3 or any integer. Okay. Like if a compound contains 2 pi electrons, then we can write this as 4 into 0 plus 2. Okay. So, here n equal to 0. So, this is 4n plus 2. So, this will be aromatic. If we have 6 pi electrons, that is 4 into 1 plus 2, that is 4 plus 2, so 6. In this case, n equal to 1. So, this is also 4n plus 2. This is aromatic. Now, if we have 4 pi electrons, so it can be written as 4n plus 2, right? 4 into 1 plus nothing. So, this cannot be aromatic. Okay. For these type of compounds which contain 4n pi electrons, they are called anti-aromatic. Okay. So, the compounds that contain 4n plus 2 pi electrons, they are called aromatic, and the compounds that contain 4n pi electrons, they are called anti-aromatic. For anti-aromatic compounds, rule 1 and rule 2 remains the same, but the difference is in rule 3. Rules 1 and 2 are same. Okay. So the difference is rule 3. So these set of rules are known as Huckel's rule. Okay. These set of rules are called Huckel's rule. So let's see some example. First is benzene. Okay. So benzene has 3 pi bonds. One bond means 2 electron, right? One bond is 2 electron. So 3 pi bonds means 6 pi electrons. 6 pi electron is 4 into 1 plus 2, that is 4n plus 2. So aromatic. Okay. Now if we have this ring, this is cyclopentadienyl anion. Okay. In this case, there are 2 pi bonds. Therefore, 4 pi electron and there is a negative charge. So, negative charge will means 2 electrons. Now, negative charge can also be delocalized. It can also form conjugation with the double bond. Okay. So, this is also aromatic because there is a total of 6 pi electrons. Okay. Now, if we have this is cycloheptatrienyl cation. Okay. So, this also has 6 pi electrons due to 3 double bonds. So, this is also aromatic. Now, in this one, if we remove the negative charge, it becomes this. This is cyclopentadiene. Okay. This was dienyl anion, this is diene. Now, this has no negative charge. So, there are only 2 pi bonds which makes 4 pi electrons. Now, this is 4n pi, right? That is 4 into 1. So, now this is anti-aromatic. Okay. But remember that first of all, we have to ensure that all these molecules are cyclic and planar. Okay. So, there are some other examples as well, like the compounds with fused benzene rings. This is naphthalene with 2 fused benzene rings. This is 1, 2, 3, 4, 5. 5 pi bonds, therefore 10 pi electrons. 4 into 2 plus 2, where n is equal to 2. So, this is 4n plus 2 pi. So, this is aromatic. Okay. So, this was the discussion of aromaticity of different compounds. In the next lecture, we will study about the preparation and properties of benzene. Thank you.